We have 4 different calculation modules in Hydrate modeling calculations in HydraFLASH. This includes THI requirement calculation, hydrate dissociation, hydrate amount calculations, and KHI hydrate line. Like other calculations, when a fluid has been introduced, tuned or characterized, it can be used to perform any hydrate calculations, any of these calculation modules. The only important thing to remember is that when you are performing a hydrate calculation, water must be in the system. Otherwise, so if you don't have water in the system, no hydrate forms. So you need to remember when you are creating fluids for hydrate calculations, you need to add water to the system. Okay, so let's assume that you have created a natural gas fluid and water or brine or a solution of milk and water, and you have introduced that fluid to HydraFLASH, and you want to perform any of these calculations. I'm going to introduce what are these calculation modules. The first one is the hydrate dissociation calculation. Hydrate dissociation point is a temperature or pressure where at the hydrate starts to dissociate. So, for example, for that natural gas, if you're working at say 5 degrees, the dissociation pressure is 120 bar, for example. That means that at pressures lower than 120 bar, the hydrates are not stable. But at pressures higher than 120 bar, hydrates are stable. So dissociation conditions are the conditions where the hydrate starts to dissociate. So if the temperature is lower than the dissociation temperature, then the hydrates are stable. If it's higher than dissociation temperature, hydrates are not stable. So one of the features of hydrate dissociation calculation is predicting the hydrate dissociation point at given temperature or pressure. It also predicts the phase equilibrium of the system at those conditions. So it not only gives you the dissociation temperature or pressure, it predicts the phase equilibrium of the system at that point, at that conditions. And by phase equilibria, I mean the fluid phase properties and phase compositions, including hydrate phase compositions. So you know how much how much will be the composition, the mole fractions of different hydrate formers in the hydrate phase. The other feature for this module is a hydrate phase boundary. Hydrate phase boundary is simply a line which divides the PT diagram into 2 regions, the hydrate stable zone and the hydrate safe zone. By hydrate safe zone, I mean the zone that hydrates are not stable, and in a stable zone, in a zone that at those conditions and those temperatures and pressures, hydrates are stable. It doesn't mean that at those conditions hydrates necessarily form, but it only indicates that at those conditions hydrates are stable. Okay. So the next one is the hydrate amount. So for example, you are working under the condition at a temperature or pressure where at hydrates are stable. It calculates how much hydrate, how much mass of hydrates you will have in the system at infinite time. And by infinite time, I mean equilibrium condition. And equilibrium conditions happens in an ideal mixing pattern and an infinite time. So, for example, if you have in a cylinder, if you have natural gas and water, and you change the pressure and temperature so that the hydrates are stable, and you let this cylinder be there forever, and or rock this cylinder and then let it be forever, that will give you the mass of hydrate that formed in your system. The other feature of this calculation is that it tells you how much would be the amount of hydrate when also wax are present in the system. As far as we know, HydraFLASH is the only software which can predict the amount of hydrates and wax when hydrates or wax are present in the system at given temperature and pressure. So in a hydrate amount, this module predicts the amount of hydrates formed at given temperature and pressure, as well as the phase equilibria of the system at those conditions, including the fluid phase compositions and fluid phase properties. The next calculation module is the KHI hydrate line. KHI hydrate line, KHI stands for kinetic hydrate inhibitors. So when you have a kinetic hydrate inhibitors, and when you measure this value CIR in a lab, and you know this value CIR for that KHI, you can perform a hydrate line when the KHI present in the system. I'm going to talk about that when I'm actually performing calculations shortly. The next module is a THI requirement. THI stands for thermodynamic hydrate inhibitors. And by requirement, it means that, so imagine that you are working on a temperature and pressure, and at those conditions hydrate are stable. So you need to know, you want to know, okay, how much inhibitor, how much THI, thermodynamic hydrate inhibitors like alcohols, methanol, or MEG, you need to use, you need to have, or you need to inject so that you work safely outside of the hydrate phase boundary. So you inhibit hydrate formation. So by giving the composition of the system here, and the temperature and pressure of the system, and the inhibitor you want to use, so it's either MEG, ethanol, methanol, whatever it is, it gives you the concentration needed to be in the system at a specified safety margin. Some people takes 3 degrees for safety margin, some people for 5 degrees. So in this calculation module, you enter first the fluid, the composition, the safety margin, the type of the inhibitor you want to use, and the given temperature and pressure, the working operation conditions of the system, and it predicts the THI concentration you need to have in your system. And then from this concentration, you can, and having the flow rate of your fluid inside your pipeline, you can calculate the dosage rate. Okay, so we have talked about the hydrate calculation modules in HydraFLASH. Now I'm going to show you how you can actually work with these features and perform hydrate modeling calculation, either hydrate dissociation line, THI requirement, how to calculate the amount of hydrates, and the hydrate line predictions in the presence of KHI. Okay, so if you remember from the presentation, I mentioned that in order to perform any hydrate calculation, water must be present in the system, because hydrates are formed when water and some other small molecule gases are present in the system, that they can form hydrates. So if you don't have water in the system, the hydrate won't form. Or if you won't have any hydrate formers other than water, it doesn't form hydrates as well. So if you have, for example, a mixture of water and hexane, that doesn't forms any hydrates, because hexane doesn't form any, it's not a hydrate form. And or if you have a live oil flowing um, through a pipeline and it has it doesn't have any water, any mist, then it won't form hydrates because it doesn't have water in it. So in order to perform any hydrate calculation, you need to add water to the system. Okay. So when you create your fluid, you have this composition here. So I want to review what was the composition for the natural gas I created. So this is the edit fluid menu, and I choose from this drop down menu the natural gas. Okay, so it's 86 mole percent methane, but as you can see, I don't have any water in it. So I want to add some water to this natural gas and see and perform some hydrate modeling. So what I need to do is to either, as explained, add water from here, or, sorry, water from here, this menu, or from the chemical solution where I can make any solution and then add the whole solution to this composition. So what I need to do, I prefer to perform the modeling using here. Okay, so this is the natural gas. Imagine that this is the composition of the natural gas flowing in a pipeline. And I am injecting water, just imagine a system. I'm injecting water to the system with around, for example, 1 kilogram of water per hour. So for example, 1 kilogram of water to the pipeline, and I want to calculate the hydrate phase boundary for the system. So what I need to do is I chose water, so my solution is only water, and I add 1 kilogram of this solution, whatever I have here, 1 kilogram, to this mixture. So I add this, and then I have a composition. I can normalize it. I will normalize it now. So you can see when I normalized it, and the sum of the amounts, the moles, is 100. Now I can call all these values mole percent. So now you can see that with adding 1 kilogram of water to that system, I have now 35 mole percent of water in the system. So that's fine. And I will call this natural gas plus water. The sample type is dry. No, it's not dry anymore, it's wet. So because this is a new composition, I save it as a new composition. Would you like to create another fluid? No. Okay. So now I have a composition which has methane, other methane, ethane, propane, as carbon dioxide, nitrogen, the hydrate form is, as well as the water. So I can perform hydrate calculation using this fluid. Okay. So to perform any hydrate calculations, you need to, as usual, navigate to the calculation tab, and then you have this section here. You have 4 modules in the hydrate calculation section: hydrate dissociation, THI requirements, hydrate amount calculation, and KHI hydrate line calculation. Let's start with hydrate dissociation. So when you want to perform, just click on this one, and then all these features and options regarding to the hydrate dissociation will appear in this panel. So you have these several options. I'm going to explain which is which. So this first drop-down menu lists all the compositions you have in the active database. You can find which database is active, or you want to change it in the database management tab or the fluid management tab. See? And in database management tab you have here. So let's go back to the calculation. So I choose natural gas and water. Okay. So the temperature and pressure units for this calculation, I prefer it as centigrade and bar. The hydrate structure detection. Okay, so this is one of the unique features in HydraFLASH. And the reason is that you can either force a system until, okay, I want to know what is the hydrate dissociation, assuming that only a structure 1 forms. Or no, I want to know the dissociation conditions, assuming that only structure 2 forms or structure H forms. Okay, so this is kind of forcing the system to form a specified structure. But sometimes you're not sure which structure is the more stable structure. For that cases, you need to tick this box, and then you don't need to know. HydraFLASH with with the thermodynamic criteria recognize the most stable structure for any condition, for any pressure and temperature, and we'll assume that, okay, because it recognizes that stable structure, then the predicted structure will be the most stable structure. So the default status of this checkbox is checked. So leave it as here, unless you want to force the system to structure 1 or structure 2. This is particularly useful forcing the system in the KHI calculation. So we don't want to do that at the moment. So for a general hydrate dissociation calculation, just take the automatic structure detection as a default or leave it as checked. Okay. So now you have 2 other radio boxes in terms of programming languages. So radio box here or checkbox here. So one is the point, which you can calculate the dissociation temperature or dissociation pressure. So you have the pressure and you want to know for this composition what is the dissociation temperature. You enter the pressure, you press run, and it gives you the dissociation pressure. Temperature. So it's temperature search because it's searching for dissociation temperature. So let's do that. You will see now the hydrate dissociation temperature search is now 16 degrees. Okay, I will explain these results here later. I just wanted to show you this these options first. Okay, let me close that. Or if you want to do the pressure search, searching for this dissociation pressure, you enter the temperature. So for example, my seabed temperature is 4 and I want to know what is the dissociation pressure. I press run. Okay, 10 bar. So that is the dissociation pressure. Good. So this is the point option. So you either choose temperature search or pressure depending on what is the known variable, known conditions that you have. Is it temperature or is it pressure? Which one is fixed? Usually it's the temperature search because it's a pressure search because you know the seabed temperature. Sometimes you know the temperature of usually for offshore cases, you know the temperature. You know the temperature of the seabed temperature, and you want to know what is the pressure. You want to know what is the maximum allowable pressure that we can work safely outside of the hydrate phase boundary. Okay. The other option is the line range. So line range, what it does, it predicts the hydrate phase envelope of a system. And what is a hydrate phase envelope? It's a line which divides the PT diagram into 2 sections, the safe zone and the hydrate stable zone. We have explained that in the briefly in the presentation. So let's calculate the line range. So this line range is performed over a range of pressure. So I just need to add a range of pressure. So I'm working between 5. I want to know between 5 and 700 bar. I want to know the hydrate dissociation curve over this range. And 10 bar incremental steps of 10 bar it's okay for me, so I press run, and this progress bar is showing the progress of the calculations. So now I have the hydrate phase boundary ready here. Okay, so what is this height? As I said, it is a line dividing the PT diagram the PT diagram into two regions. The hydrostable region is here. The temperatures below these temperatures, below the temperatures of this line, and the pressures higher than the pressures of these lines. So this is the, here on the left side of the hydrate phase boundary is the hydrostable zone. And the left side of the hydrate phase boundary, and the right side of the hydrate phase boundary is the safe zone. So if you're working at these conditions, you will not form hydrate for sure. However, you need to remember that if you're working at these conditions, you may form hydrates, depending if you're at equilibrium conditions, but you need to remember that the blockage doesn't necessarily happen. If you want to know what is the difference between forming hydrates and the conditions where hydrates are stable, or the cases when the blockage is, the possibility of blockage is there, please attend our online courses or give us an email. Just send an email to us, then we can instruct you how you can get more information about that, because we conduct we hold many online courses. It's totally free of charge, and you can learn more about this. Okay. Now you have calculated the point at the hydrate phase boundary, so you have these options here. Again, if you have watched the saturation properties, I've shown you how to work with these graph options. You can export it to an Excel file, you can export an image of this graph, or you can export the numbers of these points. You can also see the calculation results, the feed composition, the dissociation temperatures, the pressures, the molar phase fractions at each condition, and the most stable structure. So as you can see for this fluid, because you have propane, ibutanol, and pentane, the most stable structure is structure 2. But if you had like more CO2 or methane, the most stable structure will be a structure 1. But for this case, is the most stable structure is structure 2, and I didn't force the system to form a structure 2. It's automatic, and HydraFLASH is telling me that the most stable structure is a structure 2. Okay, so you can export these data to an Excel file by pressing this one, giving a name, giving a path. I've done that in the previous videos, and then you can export the file, or you can save this data to database and hide it. Now you can choose a name and then press save. That will be saved on the database, as you can see here. Okay, or you can convert the units. Okay, so let's go back to the graph. You can see that for this graph you have two subgraphs. You have two sub tabs, and in one tab you have all the information and data, and in one graph you have the visual graph representation of these data. Okay, you can zoom in, you can zoom out, you can zoom in the axes by scrolling. I have explained that in the saturation videos. For more information, please go to watch the saturation videos again, and then you can press fit to view. If you have any experimental data, you can add this to compare the predictions with the experimental data, or when you have working conditions and you want to just have a visual of where are you in terms of the height of the stability zone, is just press add, and it shows you that you are actually working inside the height of the stability zone. You can remove this graph, you can remove the added point, you can remove the hydrate phase boundary, you can clear the whole graph, or if you want to change the units, you just need to choose the units here, for example PSI G and Fahrenheit, and then convert to units, and then the units are converted now to PSI G and Fahrenheit. Okay, so this is basically the hydrate dissociation line. Let's go back to the point and try to figure out what are the results you will see in the result panel. So again, so my seabed temperature is 4 degrees. I want to know what is the maximum allowable pressure to stay safe outside of the hydrate phase boundary. And then I press run. Okay, there you go. So in this, you have different sections, right? So you have an information, the calculation type, the composition name, and then the temperature. The most stable hydrate structure is predicted to be structure 2, and the predicted hydrate dissociation pressure is 10.2 bar. Okay, so you have the compositions of the phases here. You have the composition of the feed. You have the composition of the vapor. You have the composition of the liquid phase, which is liquid phase, because you have hydrocarbons, everything, and water. So it's not. We don't really know if we can call this an aqueous solution. So we call it a liquid phase, which is 99% water, and also the hydrate phase. You have the overall composition in the hydrate phase. As you can see, you have 88% water, methane, ethane, these are all the mole fractions in the hydrate phase, and the proportion of the occupancies in the small cavities and the large cavities of the hydrates. So large cavities, as you can see, the small cavities are filled by methane and CO2 and nitrogen, because these are small molecules, and large cavities are occupied by methane and heavier compounds. If you want to know more information about this, please refer to the articles in the literature or attend our online courses. Otherwise, just please send an email to HydraFLASH@HydraFact.com. Then we will be happy to instruct you how you can join our online meetings, and we can have a short discussion. Right. The other section is the fluid phase properties, like the second thermodynamic derivatives, densities, CPCV, sound velocities, viscosity, thermal conductivity, everything. You have it here. Also, you have for the hydrate phase, these properties for the hydrate phase, and the settings used to perform this calculation. Again, like other calculation, you can save this data to database. Okay, you can export it to an Excel file. Let me give okay, so I asked desktop, and this is the Excel file name I would rather to have, and then press save. Now it is writing on Excel file. Now it is done. As you can see, this is Excel file. It's already saved, so you don't need to save it, and the data is there. And then you can close it with peace of mind that you don't need to save that Excel file. Okay. Now let's just untick this structure detection. So now you need to enter which structure you want to form. Okay, let's start with the structure 2, and then I press run. It's 10. Now I want to force the system, although I know that the most stable structure probably will be a structure 2, because I have very high heavy hydrate formers here, but I just force the system to form structure 1. Now you get a warning, and it says the system normally results in formation of hydrate structure 2. Do you still want to continue the calculation with hydrate structure 1? I press yes. Now it gives me the hydrate dissociation pressure, assuming that the only structure 1 of hydrate forms. Now you can see that structure 1 for this system is the dissociation pressure is higher, and this is lower. So that means to form a structure 1 with this system, the pressure must be higher. So it's more difficult to form this hydrate, this structure of hydrate. That's basically what happens in the KHI and other kinetic hydrate inhibitors, but it's not of this video tutorial concern. So if you want more information, please send an email to HydraFLASH@hydrafact.com. Then we will instruct you how you can get more information. Okay. So this is basically how you can use Hydrate dissociation module. You can perform points. You can calculate the hydrogen dissociation pressure, hydrogen dissociation temperature, and you can get an extensive results of what is the composition, what is the fluid fed properties, what is the hydrogen dissociation, predicted hydrogen dissociation, what is the most stable structure, and then you can have a wide you can predict a hydrogen dissociation line over a wide range of pressure. And you can force the system to form a structure 1, a structure 2, a structure H. Doesn't really matter, but we recommend that if you don't know what is the most stable structure, just leave this checkbox checked. Okay, now let's perform some hydrate modeling using when inhibitors are present in the system. You remember from the beginning of the video that I added water to the natural gas by editing the natural gas fluid. So I want to do the same with the natural gas and water fluid. So I want to add some salt or inhibitors to the system. So what I need to do is that, okay, I'll say that I want to add another solution. So I remove the water from the system. That's fine. And then or I can do something else. I can choose the natural gas fluid here. Okay, I can choose the natural gas fluid here, and then I have this chemical solution, and I want to know what is the hydrogen dissociation point if I add 38% of MEG to the system. So let's make this solution. Okay, let's let's make this solution. So I need to add water, and I need to add MEG, ethylene glycol. So I have 38% of MEG and 78% of water. They add up to 100. So all these values now become weight percent because the amount is gram. Okay, now I want to add the same injection rate. So for example, 1 kilogram of this solution, of whatever this solution is, 1 kilogram of it to this natural gas, and I just press add. Okay, now the total amount is 143. So I want to normalize it to see what is the solution, the normal. So it says that 60% of this solution is methane, 27% more percent of it is water, and 3 more percent of it is MEG. So I'm happy with the results. So I just change the name to natural gas plus water and 38% MEG. Okay, so it's not dry, it's wet, and the solid type is water and natural gas. Everything is okay, it's uncontaminated. So, and I can save it as a new fluid. There you go. And then so I have this, I want to perform a hydrate phase boundary calculation. So I press this button. I want to do phase boundary, so line range between 5 bars, or let's change it to PSIG, and Fahrenheit, or maybe centigrade. Okay, now Fahrenheit is fine. So between 100 PSIG and 10,000 PSIG, and I'm happy with 100 PSI's steps. So, and I don't know what is the most stable structure, so I leave this tick box ticked and checked. So and then I just press run. Okay, so this is my phase boundary, and I want to compare it now with when I didn't have MEG, and I want to see how much MEG shift the hydrate phase boundary, how much inhibition I got from adding 38% of MEG to the system. So what I need to do is to choose natural gas plus water, because this is only pure water. So, and then run the same calculation. So I didn't change anything. I just choose different fluids. And that was so fast. And so it asked me whether I would like to add this new graph to the current graph. Because I want to compare these two graphs together. Yes, I want to have it in the same graph. So I need to press yes. If you don't want to see them together, you just need to press no. But because I want to compare them, now I press yes. Now you can see two graphs together. The green one is the hydrate dissociation of this natural gas in the presence of pure water, condensed water. And then when I add 30% MEG to it, it shifts the hydrate phase boundary by around, so this is 70.8 and here is 88. So by around 18 degrees of Fahrenheit, it moved the hydrate phase boundary. So let's change it to the centigrade and bar. Yes, okay. So you can see that now at, for example, 600 bar, the dissociation temperature is 21, while when you don't have MEG is 31. It's quite high. So for example, 200 is 14 and it's 24. Okay. So now you have this data, you have compared them, then you have two tabs because you added two graphs to this graph, and then you have two data sets of data here, and that's fine. Okay. I don't think there will be another thing to explain, so we can go to the next hydrate calculation model. Okay, now let's start working with the THI requirement. If you remember from the previous example I talked, let's perform it again. Okay, so I have two fluids here, natural gas plus water. Let's have the hydrate phase boundary with this system. Okay. So when maybe 1 bar is just a lot, so let me change it to 5. Perform it again. Okay. So I am at seabed. I'm at seabed temperature. I have my working conditions, which is 4 degrees, and I'm working at around 120 bar. So this is my pipeline pressure, and this is the seabed temperature, and then let's add it. Okay. Now I can see that I am within the hydrate stable zone. So, and this is dangerous. The risk of blockage is higher. It's not certain, but it's high. So I want to know also. I know that I need to inject and add some inhibitors to the system. Okay, but the question is, how much inhibitor do I need to add to the system? 2%, 10%, which inhibitor? Okay, now from the engineering, I have told that, or because of the environmental consideration or other considerations, they have told me I cannot use methanol or ethanol or TEG or MEG or other thing, and I can only use MEG. So I know what inhibitors I have, but I don't know how much inhibitors I need to inject. Is it like 2 weight percent methanol in the aqueous phase is enough? 10, 15, 13. Okay, let's guess. Let's guess. I have created this 38% MEG in the system, and let's see if I'm still in the hydrate phase boundary. Yes, I want to add this to the graph. No, still I'm inside the hydrate phase boundary. Let's add more meg. So I remove this, and or maybe it's better to choose from the natural gas. Okay, and then so 30% meg, I was still outside of the hydrate phase boundary. So what I need to do is to add more meg. So let's try with 40% meg. Right, and then again I add 1 kilogram of this to the solution, normalize it, and then I change the name plus water 40 weight percent meg, and it's wet, and save as name. No, okay. So let's try with 40% meg. Add this. Oh, okay. So I'm still inside the hydrate phase boundary. So you see, it's difficult. You need to just guess, and then sometimes you fall too outside of the hydrate phase boundary. Sometimes you see. So to save time, you can use this module, THI requirement. So you are trying different concentrations of meg to see what is the minimum required inhibitor of meg. What is the minimum required meg that you need to have in the system to at least your working conditions become your dissociation temperature, right? Or with a safety margin, you want to work 3%, 3 degrees, 4 degrees, 5 degrees outside of the hydrate phase boundary. To do that, it's a simple thing. You just need to press THI requirement. You only need to have some meg in the system. So you only need to have some meg in the system, and this is the main features of the THI requirement calculation module. So these are the units, the temperature, pressure. I'm happy with the units. The hydrate structure detection is automatic, so I leave it as it is. The inhibitor I have decided to use is meg. If it is methanol, then you need to choose methanol and add methanol to the fluid. If you don't have methanol and choose methanol, if you don't have methanol in the fluid and you choose methanol, you're gonna receive an error. So because I have meg in this fluid, so I choose meg. The inhibitor quality, so for now, is 100. So I assume that the inhibitor I'm using is pure. Okay. The production is none, so I just leave it as it is. I will explain what is it now. So the water rate and the WGR is now deactivated, and the safety margin. The safety margin is the delta T, is the difference. It's the actually the distance you want to be away from the hydrate phase boundary. So it simply means that, okay, so how far you want to be from how far from the hydrate phase boundary you would like to be, and be in the hydrate safe zone. Okay, so this tells me this. So let's now tell HydraFLASH that I want to be 0. So that means that I want to be exactly on the hydrate phase boundary. So because if you notice that when you add meg, you are moving through this point. You're moving to the left side. And I want to know what is this critical meg concentration, so that the hydrate phase boundary and the operation condition falls exactly on each other. So I enter the safety margin as 0. Okay, and my working conditions is it was 4 degrees and 120. So I'm happy with everything, and now I press run. Okay, I will explain the other results later. Now it tells me that the THI weight percent in the aqueous feed needs to be 44.52%. So I just copy this number, right? I just copy this number, and then I create another fluid. So by trying new values, now I know the critical MEG concentration. So I make another solution. Water, MEG. This is the concentration of MEG. For some reason it doesn't copy. Okay, let's enter it by hand. So 44.52 2881. Okay, now so I'm not sure. Let's open an Excel file. That what would be the okay, so 100 minus this value is 54. Okay, 55.47. Again, let me look at that. 47.71. 71. Now this add up to 100. Okay, now I add 1 kilogram of this solution to this natural gas, and then I call this 44, or let's call this adjusted MEG weight percent of MEG, then save as a new. No. Okay, so let's now calculate the hydrate phase boundary with the adjusted weight percent. So from 5 to 500 and then plus 1. Okay, now yes. Now, as you can see, now the hydrate phase boundary falls exactly right on my working conditions, my operation conditions. So instead of adding just gradually a little bit of MEG, and then see actually where I am, and then trying so many hydrate phase boundaries with one single calculation and entering the working conditions, it told me that you need 44% MEG to work exactly on the hydrate phase boundary. Now I tell HydraFLASH, no HydraFLASH, I want let's go back to the 30%. I want 3D. I want to work at least 5 degrees outside of the hydrate phase boundary. So what I can do is that I enter the safety margin as 5. My working condition is 4 degrees and 120 bar, and then I press run. Okay, now it tells me if you want to work safely 5 degrees outside of the hydrate phase boundary, you need to inject 51% of MEG. Let's calculate the hydrate phase boundary. Let's make this fluid again. So this is the fluid. I just need to calculate and then so this will be the water concentration. Okay, so this is the MEG concentration, and let's remove water from this one and add a new MEG and water. So this is my MEG concentration, and this is my water concentration. It adds up to 100. I want to add 1 kilogram of this to the solution. I do that. I just need to change the name. and I call this 5 safety margin, 5 degree of safety margin, 8% meg. It's bad, so everything all happy with it, and then save as new. Okay, no, let's expand this, and then in this graph I want to calculate the hydrate phase boundary, so I go to hydrate dissociation 1, and then on the line range I, starting from 5, I calculate the hydrate phase boundary. Okay. Now, as you can see, HydraFLASH, this module told me that if you want to work 5 degrees outside of the hydrate phase boundary, you need to inject 51% meg. I did that, and now this is my graph. So I added 51% meg to the system, and now my operation condition, which is this point, is 5 degrees, exactly 5 degrees outside of the hydrate stability zone. So this is basically why this calculation module is very useful. So let me just clear everything here. Okay. So I just wanted to show you why why and how you can use this module, and how effective and actually be an efficient way of working out how much THI you need to inhibit the system safely. So again, I just want to introduce the let me close this Excel file. Introduce the features. The first drop down is the fluids, the units, the selected units. As I explained, that you need to tell HydraFLASH which inhibitor concentration you want to optimize and you want to adjust. And the inhibitor quality is usually for they use very pure methanol. For methanol is very pure, but you always have this purity that is given by the provider. So let's assume that, for example, is 99 for meg, for example, and the production. So what is this? It's basically you're saying that, okay, what is the production? Is it gas that you use as a main production, or is water? So I used gas, and I said that, okay, I'm producing 10 million standard cubic feet per day of gas, and the water rate coming with this gas is, for example, it's 2 barrels per day, and the WGR of this gas is, for example, 5. It's a number, whatever you have, and the safety margin is. And then when you perform this calculation, let me cancel this because this is too much. Okay. Now, using the parameters, the production parameters you entered here, HydraFLASH tells you that required inhibitor supply rate, how much would it be? So it does the mass balance for you. It just does the calculations for you, that you need to know how much standard barrel you need to inject per day, depending on the production rates you have entered here. So whatever your production rates are here, you need to add them here, and then you provide the safety margin, and then it works out how much of the THI you need in the system. So for example, for working these conditions, you need 41%, and then that means that you need to inject 33 barrel of inhibitor per day to the system. If you add this dosage rate to the pipeline, you will have 41 weight % in the water phase inside the pipeline. So what is this percentage I'm talking about? 51%, 41%, 30% is the concentration of the inhibitor inside in the water phase inside the pipeline. So by knowing the mass rate of the water phase and knowing the required concentration of meg inside that water phase, you can work out how much you need to actually add meg to the system. By the way, HydraFLASH does that for you, and it tells you that you need to add 33 barrel per day. The other part of the report, as usual, is the phase Equilibria calculation. For these conditions, the temperature, safety margin. So the safety margin, 5 degrees is the temperature safety margin. So that means that it is actually the phase equilibria for 2 degrees. Because it's a safety, it's 3 degrees inside. So this is the phase equilibria for the temperature minus the safety margin. And then so you have the feed, the vapor phase, the aqueous phase, and the hydrate phase, and the occupancies and the composition of the water phase, and the fluid phase properties, and the settings you used for this calculation. Like other calculation, you can always export the results to an Excel file. I will choose my desktop, and then I choose a name for this. So I put this THI results. That will be the name of the file, and then I press save. And now a saved file now will appear here. So I just close this. We can save this to the active database that you can access before, and then you can convert the image as usual. Okay. Now we have talked about the hydrate phase boundary calculation and THI requirement. To first, for hydrate dissociation calculation, we wanted to know that at which conditions the hydrates are stable, and the hydrate THI requirement was designed so that it tells the user how much inhibitor is needed to inhibit hydrate formation in the system. Now imagine we are inside the hydrate phase boundary and we want to know how much actually hydrate we form. To perform this calculation, you need to click on the hydrate amount calculation. It tells you that in equilibrium condition, which assuming that the mixing pattern in the system is ideal, and you give infinite time to the system to equilibrate, and at that conditions, how much will be the amount of hydrate formed in the system. So let's perform a hydrate dissociation line calculate, for example, for this system between 5 degrees and 500 bars to see what is the hydrate phase boundary. Okay, now it tells us that in this region, the hydrates are stable. So if the PT falls inside this region, then the hydrates are stable, and if it falls inside this region, the hydrates are not stable. So let's imagine we are working at this condition at, for example, 4 degrees and 100 bar. Okay. Now it says that we are inside the hydrate stability zone, and we want to know, okay, how much hydrate will form and how percentage of the mass of the system total fluid goes to the hydrate phase. Okay, now we can do that by performing a hydrate amount. And don't forget that this value predicted by this module predicts the amount of hydrate in equilibrium conditions in the ideal mixing pattern and infinite time. Okay, so again, like other calculations, you have a drop down menu here. You can choose the fluid, and like other hydrate modules, you need to have water and hydrate forming components in the system. So I choose this one. The temperature and pressure units, the phase distribution. You tell HydraFLASH whether you want to know how much weight percent, mole percent, weight fraction, or mole fraction of the system is hydrate. And the hydrate structure detection is automatic. We explained that in the hydrate dissociation calculation, so I leave it as automatic. And also you have these two options to tell the engine, the thermodynamic engine, whether the wax phase can form at these conditions or not. Or you want to consider the existence of wax in the calculations or not, because this is a natural gas, and we know that natural gas, it's a very light natural gas, so it doesn't form a wax, so I leave it as no. And ice phase, I prefer not to include the ice phase as well in the system. So, and I want to know how much hydrate at this condition I will have. So what I need to do is to enter the conditions, 4 degrees and 100 bar, and press run. Okay, now you see the result. It tells us two values: the hydrate weight percent of the total feed. That means that how much of the weight percent of the total feed is actually hydrate, which is around 13 weight percent of the feed at that conditions will be converted to the hydrate phase. And also this value, it's the water weight percent converted to hydrate. That means that the total weight percent of water, converted to the hydrate. So that means that 30% of the water I had in the system was converted to the hydrate. Okay. The other section is the phase compositions. You can see that what is the feed composition, what is the composition in the vapor phase, what is the composition in the aqueous phase, and what is the composition of the hydrate phase. Also, it tells you what is the molar distribution, how much is the mole fraction of the vapor phase, which is 67%. So that means that 67 mole percent of the system is in vapor phase, 18% of it is in the aqueous phase, and 13 mole percent of the system is actually hydrate phase, and as well as the other properties like the compressivity factor, second thermodynamic derivatives, and viscosity, etc. Okay, and in the last section you will have the settings for this calculation. Like other calculation, you can save these calculations on database, you can export it to Excel, or if you want to convert all the units, you can do that by this option. Okay. Now let's close this one and then try to be outside of the hydrate phase boundary. So if my working conditions is at the same temperature, 4 degrees, but my pressure is much lower, for example, is like 20 bar. Now you can see at 20 bar, I'm working outside of the hydrate phase boundary. So if I enter this condition, 4 degrees and 20 bar, into the hydrate amount calculation, and I press run, it tells me that no hydrate predicted. And you see that dashes in the hydrate phase, and you don't have any hydrates formed in the system. So it gives you a worst case scenario of how much hydrate you will have in an infinite time in the system if the entered conditions falls inside the hydrate phase boundary for this system, for the fluid that you have entered. If you want to see the changes in the hydrate amounts, you can use the hydrate amount curve. So if you want to fix the pressure and see, okay, at 100 bar, if I change the temperature from -10 to 30 by one incremental step, what is the changes in the amount of hydrates forms in the system? And then press run. Now it tells you from -10, where you have 21 weight percent water, when you're heating up the system, the amount of hydrates you will have becomes less, and then at 11 degrees, which is around here, then the hydrate phase disappears. So that it shows you the trend, the changes of the amount of hydrate forms with increasing the temperature of the system. And you will have the data for this graph, the weight fractions, the composition, and the settings here. Again, you can save this to database, export this file, or convert the units. But you need to remember this graph, the y-axis is the hydrate amount, weight percent, as I specified here, and this is the temperature. If I perform a temperature fixed, if I want to know if I'm working at pressure at 4 degrees, and I change the pressure from 1 bar to 200 bars with let's say 10 incremental step, what would be the changes in the hydrate amount form in the system? Okay, now I want to create a new tab. So it tells me that at 4 degrees, sorry, by changing the pressure from 40% up to 200 bars, the weight of hydrates formed in the system increases because I'm increasing the pressure of the system. And when I'm increasing the pressure of the system, I'm forcing the hydrate formers to form hydrates because I'm favoring toward hydrate formation, favoring the conditions of the system toward hydrate formation. So again, this was the changes in the hydrate when I fixed the pressure and I changed the temperature. And this is the changes in the amount of hydrate when I fix the temperature and I increase the pressure. Okay. So this is basically useful when you want to know whether if you are working inside the hydrate phase boundary, you would have the risk of blockage or not. This is not very straightforward thing to decide. However, to have more information, we suggest that you attend our online free courses. We explain a case study where using this module, you will able to know whether you block sometimes, or you can decide at which pipeline, which condition you will experience blockage and what is actually happening in your system. Okay. Now we talked about the hydrate dissociation predictions, the amount of THI you need to use to prevent hydrate formation. Now it's time to have a look at the Khi line calculation. Khi stands for kinetic hydrate inhibitors. If you want more information about the KHIs and how you can use them to inhibit hydrate formation in the system, please send an email to info@hydraflash.com, and my colleagues in the KHI team will be able to help you. Okay, but this module, this is, to our knowledge, HydraFLASH is the only PVT package in the market that can give you an estimation of how much KHI can be effective for your system. Okay, so again, in these calculations, we are assuming that you have some KHI in the system and you want to know how much that will affect on the hydrate phase boundary. So what I need to do is that, again, like other calculation modules, you have this drop-down menu, you have these units, you want to know what is the KHI dosage, the density of the KHI, the aqueous phase rate or water phase rate, and then the CIR. This number CIR is the number that needs to be measured experimentally through the lab. So it's like one of the characteristics of the KHI you're using. So you cannot model this value. It needs to be experimentally measured, and then you can use this number to predict the inhibition effect of the KHIs, and you need to enter this. You need to kind of see these effects on its effect on the hydrate phase boundary. So I want to know, for example, for this natural gas and water fluid, I only have natural gas and water, and I have a KHI with the default signatures and the CIR of 5 Kelvin, and I want to know what will be the effect of the KHI on my hydrate phase boundary. So what I need to do is to specify a range and then press run. So this is an important message you need to have a look. This is, for this calculation, the experimentally measured complete inhibition region, CIR, complete inhibition region, for the KHI is necessary, as I mentioned, that you need this value to be measured experimentally. The purpose of this feature is to provide an initial estimate of if KHI can be an option for preventing the hydrate formation. Please note that further experimental investigation is required to make sure KHI can provide the necessary inhibition. Please contact us for further information, and use of KHI on its own is not recommended for temperatures below 0 degrees. Okay, so this is a warning message, and I press OK, and software starts its calculation. Okay, press OK. So now you can see two hydrate phase boundaries. The first hydrate phase boundary, the blue one, is the Hydrate line natural gas, which is the hydrate phase boundary of this system at a specified pressure range. And this would be the hydrate phase boundary of the system in the presence of this KHI with this CIR. So you can see that this KHI shift the hydrate phase boundary to the left side. So that means that it is working and it may be an option. So it gives you an estimation, but again, below 0 degrees, you see this hydrate phase boundary is not predicted for below 0 degrees. So for below 0 degrees, it is not an option. And but you can see that, okay, it is an estimation, it may work, but let's investigate further. So when you do this, you need to contact us. Then my colleagues in KHI team will be more than happy to help you on this. Again, like other calculations, you can work with this graph, you can zoom in, you can fit to view, you can add points, convert units, clear the whole graph, or remove one of these data or any added points from the graph. You can export the data to the Excel file and export to an image file. And you can also see the data for these graphs here. Again, you can save them to the database, you can export them, and or you can copy them to a text file or whatever you have. Okay, so again, we have explained the hydrate dissociation, and an overview was that the hydrate dissociation is used to predict the hydrate dissociation points or the hydrate phase boundary for the active fluid. The THI requirement tells you how much inhibitor you need to inject to inhibit to work safely outside of the hydrate phase boundary. The hydrate amounts will predict the amounts of hydrate that will form in an infinite time in an equilibrium conditions, which is an ideal condition, and how much hydrate you will have in the system if you are working inside the hydrate stability zone. And the KHI line, it gives you an estimation of the effectiveness of KHI with the specified CIR in your inhibition strategy.